Hi everybody, Physics Ninja here. Today we are going to do a review on center of mass problems. So I've got 4 problems for you to work out. We're dealing with problems where we're calculating the position of the center of mass. For example, you could have people walking on a plank or on a boat. One might be just to calculate the coordinates of the center of mass if you're given some coordinate system and some origin. We have another one here that's kind of similar to that. What if I cut out a rectangular piece of a sheet of plywood, for example? How would I calculate the coordinate of the center of mass for this object? And then the last problem is I have another problem where a person is walking on a boat, and what happens to the position of the center of mass, what happens to the position of the boat, say, with respect to the shore. All right, so we got 4 problems. There's 9 or 10 questions based on these 4 problems. Now what I suggest that you do is you first download the PDF. So just click on the link in the description of the video. It'll take you to that PDF. You try the problems out for yourself. After you've given them a try, come back and watch the rest of the video. You can watch my solution, see how I solve these problems. Alright, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. Alright, let's get started. Alright, here's our first problem. We have Allie, which has a mass of 58 kg here, located on the left-hand side, and Josh is on the other side. He has a mass a little bit bigger. He's on the right-hand side. They're initially standing still on opposite ends of a plank, and the length of the plank is 5.1 meters. The plank itself has a mass of 19 kg. With Allie on the left and Josh on the right. The plank is initially at rest on smooth ice, so there's no friction between the plank and the ice. The first question says, suppose Josh stands still while Allie walks all the way to the right end of the plank to give him a hug. What is the displacement of the plank from its initial position as they are hugging? We're going to take that x direction to be to the right. So let's go see how we solve a problem like that. So this is kind of a nice center of mass problem. The first thing that is very, very important is as Allie moves to the other side over here, she walks actually relative to the plank. All right, so she moves all the way here to the right-hand side. She does not move relative to the ground. So this is one of the key points of this problem. The other really important point here is that if I look at the displacement of the center of mass of the system here, that there has to be 0 because there is no net force acting on the system. When she walks, there's a force of friction acting on her foot. There's a force of friction acting on the plank. These forces are equal and opposite, but they're not an external force, which means you have to have the position of the center of mass remain at the same place, or the displacement equals to 0. Now, how would I write the displacement of the center of mass? Well, I would write it as the mass of Allie multiplied by her displacement, and her displacement is the displacement of Allie. I'm going to write it everything relative to the ground. Okay, let's have a look at what else do we have in the problem. We have Josh here, and his displacement now, we're looking at the displacement of Josh relative to the ground. And then the last one we're interested in, what is the mass of the plank and what is the displacement of the plank here relative to the ground. Now all of this gets divided by m total, and m total is nothing more than ma plus the mass of Josh plus the mass of the plank. Now including this denominator doesn't matter for this problem because everything here is equal to 0. Therefore you could really just avoid this whole denominator because the terms are equal to 0. All right, one of the things to do now is to note that she's walking relative to the plank. So what we're going to do is we're going to substitute, for example, this term right here, and I'm going to write this as the sum of 2 displacements. So the displacement of Allie relative to the ground, my goal here is to insert a quantity that I know here, and this is going to be the plank. So the way that you write this displacement as the sum of 2 displacements is you write it as the displacement of Allie here relative to the plank plus the displacement of the plank now relative to the ground. So you're going to substitute this displacement of Allie relative to the ground by these 2 over here in my first equation up here. Let's maybe label this equation here equation 1. Now the other thing I'm going to want to do now is do a similar exchange for the displacement of Josh here relative to the ground. So Josh relative to the ground, I'm going to write it as the displacement of Josh relative to the plank plus the displacement of the plank relative to the ground. Now, since Josh stands still, right, he is not moving over here. So his displacement relative to the plank, which is this first term over here, this guy here is simply equal to 0, so you don't have to worry too much about that term. That simplifies. So let's go back to equation 1 right here and watch that. We want 0 net displacement of our center of mass. Here I substitute the mass of Ali. In my displacement of Ali relative to the ground, again, I open it up and I replace it by this. Ali relative to the plank plus the displacement of the plank relative to the ground. I do a similar thing for Josh, except Josh, I'm only left with one term. The displacement of Josh relative to the ground is nothing more than the displacement of the plank relative to the ground if he's standing still. And the last term is unchanged. It's already relative to the ground. So I write the displacement of the plank relative to the ground. So let's think about what I'm trying to solve here. This is my goal. I want to solve the displacement of the plank relative to the ground. It appears in 3 different places over here. So all you have to do then is factor out that term. Bring this term over here, the displacement of Ali relative to the plank, multiplied by the mass of Ali, bring that to the other side. So be careful with the algebra over here, but if you take your time, you should get this. The displacement of the plank relative to the ground is given by minus MA, the displacement of Ali relative to the plank, and now divided by, look at all the 3 terms. They end up being mass of Ali plus mass of Josh plus mass of the plank. And now we're in a position to substitute our numbers into this expression. So the mass of Ali is 58. The displacement of Ali here relative to the plank is basically the entire length of the plank. That is 5.1 meters. And now you have to divide by the total mass. So here you put 58 plus the mass of Josh, which is 87, and plus the mass of the plank. So at the end, look what we get. Our displacement of the plank relative to the ground, substituting all the numbers here, you should get minus 1.8, and that is measured in meters. All right, let me box that up. We go look at our choices over here, and that corresponds to choice number E right here. All right, here's the next question. It says, suppose the mass of the plank was larger, but everything else stayed the same. The distance moved by the plank would be A, the same, B, smaller, or C, bigger. Well, let's think about our expression, and where does the mass of the plank come in? It only comes in here in the denominator. So what happens if I make that mass really, really big, for example? I am going to be dividing by a bigger number, which means that this displacement should be a smaller number. So for this one, B is the best answer. All right, the next question says, suppose instead that Ali walked to the right side to meet Josh, and then they both, Josh and Ali, walked together back to the left side of the plank. Which of the following statements best describes the motion of the plank? All right, well, for the first part, we know that, look at what we got. We got minus 1.8 meters. That means when Ali walks all the way to the right-hand side, it means that the plank moves this way minus 1.8 meters. Okay, minus just tells me the direction. So it tells me that initially it moves to the left-hand side. So one thing we can get rid of is anything that says that initially it moves to the right-hand side. That's not what's going to happen. So with this, I would eliminate choice B and D because it says that the plank moves to the right a distance dr. Now think about this. Now when they both move over, right, when Josh and Ali both finish on the left-hand side, the plank's going to move in the opposite direction. However, what are we doing? We're shifting more mass here on the left-hand side. So at the end, that motion to the right is going to end up being bigger than the motion initially on the left, right? Because you're moving simply more mass because 2 people are walking down. The more mass you shift to one side is going to give you more motion of that plank in the opposite direction because we want the position of the center of mass to remain the same. So since we are moving mass, the plank will move, and the best choice here is actually choice C. The motion on the left is going to be less than the motion on the right. Okay, so that's kind of a good problem. Let's go on to the next one now. All right, here's problem 2. Two rectangular blocks each have mass m, length 2L, and a width L. They're arranged as shown in this figure over here on the right-hand side. So we want to use the lower left-hand corner of the system as the origin. So let's go highlight that. So our origin is down here at the bottom. So that's going to be important. The first question says, what are the XY coordinates of the center of mass of the system with respect to this coordinate system right here? So what we're going to do for a problem like this is you want to simplify basically complicated objects or more complicated objects like rectangles, and I want to replace them by points. And I'm going to place the points at their respective center of mass positions. Let's go ahead and write down what is the coordinate of the center of mass of this lower rectangular block. The coordinate here would be given by, well, it has an x value which is going to be L divided by 2, and it has a y value which is going to be, again, just the value L. It's always at its geometrical center. All right, how about this guy over here? What would its coordinates be of this dot here representing that upper block? Again, its x-coordinate of the center of mass for only this upper block here, you see that that's a distance L away. And its vertical here would be 2L plus whatever length this is. This is L over 2. So I would get 2L plus L over 2. Let's go ahead and just simplify that. That should be 5L divided by 2. All right, I'm now in a position to calculate the coordinate, for example, the x-coordinate of the center of mass. For this here now, I simply use the formula for discrete point masses. Oh, I can't do that. Let's try that again. You sum the masses multiplied by their coordinates, and then you divide by the total mass of the system, m total. All right, so let's go and evaluate each one of these terms. And here I'm only worried about the x-coordinates. So what do? Well, let's take this lower one to be the first one. So it has a mass big M. It has a x-coordinate of L divided by 2, and that's it. Now you go to the next term. For the upper block, we also have a mass M, and its x-coordinate is given by simply L. And now I have to divide by the total mass. The total mass is M plus M. One thing we can do now is simply simplify these terms. We notice that the masses are all going to cancel out. So what we're going to be left with here is 2 at the bottom. And at the top, you're going to be left with L over 2 plus L. That is 3L over 2. This you can write then as 3L over 4. Okay, so that is the coordinate or the x-coordinate of the center of mass. You can see right away that 3L over 4 corresponds to choice E. There are no other 3Ls over 4, so really, we're actually done the problem here. We don't have to go any further if this was a multiple choice problem. But let's go ahead. We also want to maybe calculate what the Y center of mass position is. Again, we are applying a similar formula, except now my positions, we're taking the Y coordinates here, and again, it's over the total mass, and the total mass for this system is 2M. All right, so what would this look like? Well, we do the mass M for the lower block. Its Y coordinate is L plus. The second one also has a mass M. Its Y coordinate is 5L over 2. And all of this now I must divide by 2M. Again, all of these M's cancel out. We don't have to worry about that. And now you're left with L plus 5L over 2. That's 7L over 2, and I still have this other 2 that was left over here. So at the end, I get 7L divided by 4, and that is the Y position of the center of mass, and you can see that corresponds to this guy right here. It is also the only one with 7L over 4, so you didn't actually have to calculate both of these to get to the right answer. All right, well, let's think about the next one now. It says, if the mass of the top block were decreased, but its size remained the same, what would happen to the location of the center of mass of the system? Given 3 choices here, it will move to the right and up, it will move to the left and up, it will move to the left and down. So what happens here if I reduce this one, right? And again, I'm only reducing the mass. Okay? What do you think would happen? Well, what happens if you really reduce it? What if you set the mass to 0? What happens? The center of mass of the system would then be right here. And its initial position actually is right here. It's 3L over 4. somewhere over here. It's probably right around here initially when I don't decrease this mass. But if I reduce that mass to 0, you see it's shifting here. It's shifting down, and it's shifting also to the left. Right? So in this case here, the best choice here would be choice C right here. All right, problem 3, we have another man on a boat type of problem. Here we have a boat of mass of 160 kg and a length of 14 meters is initially floating at rest with its left end next to the shore and its right end a distance L away from the shore. A man with mass of 50 kg initially stands at rest at the right end of the boat. Again, we neglect any friction between the boat and the water. First question says, suppose the man walks to the left end of the boat. As he is walking, what happens to the location of the center of mass of the man-boat system? All right, so this is really one of the key points here. When he is walking, there is no external force. If there's no external force acting on a system, that means that the position of the center of mass must remain at the same position. So there cannot be any displacement of the center of mass. It must be 0. So the center of mass does not move. So choice A is the best answer for this question. All right, the next question says, when the man reaches the left end of the boat, how far is the boat from the shore? Again, I'm going to proceed using a similar approach to problem 1 over here. I'm going to write that the displacement of the center of mass must be 0. And that displacement must be the mass of the man multiplied by his displacement. So I'm going to call this displacement of the man relative to the ground. And plus the mass of the boat multiplied by the displacement here of the boat relative to the ground. Now, one thing we have to remember here is that when he walks in this direction, he is actually walking relative to the boat, okay? The boat is actually going to be moving back. So what we're going to do here is we're going to exchange this guy here. We're going to replace this by the sum of 2 displacements. So let's proceed exactly like we did for problem 1. So we write this as m, and the displacement of the man relative to the ground, I can write it as the displacement of the man relative to the boat plus the displacement of the boat relative to the ground. All right, plus the mass of the boat and multiplied by the displacement of the boat relative to the ground. Now think about what we're looking for. They want to know how far he is from shore. Well, again, he's going to be standing over here, but the boat is going to be moving back a little bit, okay? Because as he walks, he produces a force acting on that boat. So it's going to move back a little bit. So we want to find what that distance is, and that here corresponds to this. What is the displacement of the boat with respect to the ground? Again, all we have to do now is group the terms and then simplify this expression and solve for this unknown right here. So let's do a little bit more algebra. Let me bring this all the way upstairs over here. So I can write that the displacement of the boat relative to the ground here, be careful, so we're going to bring one of these terms on the other side, minus the mass of the man, the displacement of the man relative to the boat, and divided now by the total mass of the system, little m plus big M. All right, now we're going to substitute our values. All right, so this is what it looks like. His mass is 50 kg. Now, what is his displacement here of the man relative to the boat? He's walking this way, and he's walking a distance of 14 meters. Now, since he's walking to the left, I'm going to call this minus 14, because minus is going to be my direction anywhere to the left, right? If I use just a standard coordinate system like this, or I call this positive x. Now, again, I have to divide by the total mass, so this is going to be 50 plus 160. So now we simply put those numbers in the calculator, and we get that the displacement of the boat relative to the ground, you notice it's going to be positive here once you multiply that through, and you should get a number of 3.33 meters. That's it. So go ahead and box that up. That should correspond to one of the choices, and there it is. Choice D is the correct answer for this problem. The next question says, if the man was carrying some heavy object as he walked from the right end to the left end of the boat, how would his new final distance from the shore change? Would it increase Would it not change, or would it decrease? All right, so if he's carrying more mass, again, there's more mass shifting from one side of the boat to the other, okay? Now, what that means over here, again, we already have a general equation. So what happens, for example, instead of making his mass equal to 50, what happens if I set his mass equal to 100, right? That would be shifting more mass from the right-hand side to the left-hand side. What would be my displacement here of the boat relative to the ground? Again, you would simply substitute these numbers here, divided by 100 plus 160, and what you would find in this case, for example, this would give me 5.38 meters. You notice that this here is bigger than the 3.33. Okay, so it would increase his distance from the shore. Okay, so the boat would shift more in that case. Again, the position of the center of mass does not change anymore, okay? And the way that you have to adjust for that is by moving the boat further away from the shore. All right, here's our final problem. It says, consider a thin, uniform, solid, rectangular sheet. It has a mass m, length 2L, a width 2W. It's placed symmetrically with respect to the XY coordinate system where the origin's right at the center over here. All right, now the upper right quadrant of this sheet is cut off, as shown in this figure here on the right-hand side. So this is missing here, this white area. What is the X position of the center of mass of the sheet with the missing quadrant? And note that O represents the origin here. All right, so how would we find the X position of the center of mass? Again, what we're going to do is I'm going to replace each one of these rectangular sheets by a simple point mass. And the position of that simple point mass is at the position of its center of mass. So for each one of those, it should be at its geometrical center. So I'm just going to list, there's only 3 points. I'm going to say that each of these here has a mass little m. Okay, that's it. Now go ahead and we have to define the positions of each one of these points relative to the origin right here. This is the origin. So what do we have? Well, that means that this guy here is going to be a distance of positive L over 2 that way. And each one of these is going to have a coordinate of minus L over 2. Likewise with this bottom one, minus L over 2 with respect to this being the 0 here. Now I'm not writing the vertical component because they're only asking me for the X position of the center of mass. So I'm not really worried about anything going on in that vertical direction. So the X center of mass then is simply this, right? We apply our formula. You add up the masses multiplied by their coordinates and divided by the total mass of the system. All right, so in this case, what do we have? Well, let's just start labeling these. So we have this first one down in the bottom. It has a mass m, and its position is positive L over 2. Next, I have a top one in the left-hand corner. It has a mass m, and its position is minus L over 2. Now I deal with this lower one in the left-hand corner. It has a mass m, and again, its position with respect to the origin is minus L over 2. I have to now divide by the total mass of the system. That is simply 3m. Each of these planks has the same mass. The nice thing we see is that all of these masses cancel out. That's good. The next thing we see, we have positive L over 2 and we have minus L over 2. So we can cancel out one of those. And the only thing we're left with now is that X center of mass is equal to what? Minus L over 2 divided by 3. Well, that's minus L over 6. Okay, that is the position of the center of mass. And that corresponds to choice A right here. So A is the correct answer. All right, hopefully you enjoyed this review. You enjoyed this problem. I hope you are well on your way. Good luck on your quiz tomorrow, Physics 2111 students.